Hi, this is a video about the speed of waves and how we can figure that out. And there's really two different ways in which we can figure out the speed of waves. So for example, you could measure a wave and say, hey, how long does it take a certain wave to go a certain distance? And waves typically are going to be constant speed. So if the speed is constant, you can say the velocity or speed of a wave is distance divided by time. Meaning if it goes 10 meters in 2 seconds, then your velocity would be 10 meters over 2 seconds, or 5 meters per second, right? Pretty straightforward. Imagine instead, because sometimes you'll get fooled, you might see, hey, I'm standing, let's say that you're standing here, and you shout, and it hits a wall that is, my numbers are not going to be accurate here. Let's think about this. So let's say that it hits a wall that's like 170 meters away, and you hear an echo 1 second later. And you want to figure out the speed. So again, you can go speed or velocity is distance divided by time, but keep in mind that if you're hearing an echo, the sound has got to go there and back. So the total distance is really not 170, but 340 meters, and it does it in 1 second. So your speed would be 340 meters per second. So occasionally you will have echo problems where it's again distance versus time, but you got to realize that the distance is twice what you might have thought it was originally. So that is one way to find the speed of objects. Velocity is distance divided by time. There is another way, and that comes from knowing the wavelength and the frequency of a wave. So we've also found velocity is frequency times wavelength. And you can find the equation on your reference table, meaning if your frequency is, I don't know, 20 hertz, and your wavelength is 2 meters, your speed is frequency times wavelength, 20 hertz times 2 meters, make that H, or 40 meters per second. And we'll often use this equation backwards. Say you know the velocity, you want to find the wavelength because you know the frequency also, or vice versa. There's lots of ways to work this sort of problem. A couple of kind of waves that we're going to see fairly regularly include sound waves and light waves. So sound and light waves, the speed varies depending on the medium through which they are traveling, but if you look on your reference table, you will see a speed of sound. It is given at STP, standard temperature and pressure, and it will change depending on, for example, the temperature or the pressure. But sound is about, like 340 or 343 meters per second in air. So again, that depends. Light will slow down as it travels through different materials like glass, a little bit through air, but light is about 3 times 10 to the 8th meters per second. So much, much faster than sound. And that's in a vacuum. And I'm going to put or air, because it slows down a tiny bit in air, but not a whole lot, 3 times 10 to the 8th meters per second. And again, these are both on the reference table. If you look for light, the speed of light in a vacuum has a special letter to it, and that letter is the letter C. And you'll see that on the reference table too. It pops up in things like E equals mc squared. That C right there, that's the speed of light in a vacuum. So if you want to find that, you can look for it. C is about 3 times 10 to the 8th meters per second. And again, it changes in other materials. So I think that's about it for this particular video. Double check and make sure. Yeah, the only thing else I wanted to mention is that as materials travel through different media, and we'll see this in a different video, as the speed changes, their direction of motion can change too. That is something that we call refraction. You'll see that later on, so just as speed changes as you enter a new medium, the wave can bend or change direction. That is known as refraction. And that is not to be confused with the term rarefaction, which we saw in the last video. So rarefaction is different than refraction. Once again, a vacuum is a material, is like space where there is no material, I should say. There's no air, there's no other particles, or very few. So that is it for this particular video. I'm going to step out of the way one last time in case you need to write any of that down. Thank you very much for watching.